Okay, so welcome back to the presentation of Chapter 1 of Cyber-Physical Systems. We left with DiscreteTime Systems. We already went through this slide for completeness. I'm going to pick it up at the beginning. So you all recall DiscreteTime Systems. So this is where we sample the natural world, the physical world, and then we process it mathematically. So what we get out of the signal is an array of numbers that we can essentially, with a dedicated computer or digital hardware, we can process it with equations, algorithms, and so on. So that is much closer to where we're going, because these are systems where we're going to try to sample as soon as possible, and we can do that. Today's analog to digital converters have an amazing capabilities in terms of speed, which we can sample directly the radio bands at the lower radio frequencies, but still at RF. And we can also convert from digital to analog to give back that output to the natural world to interact with the physical system. So if you recall, discrete-time systems are also linear systems, and we are able to add two inputs, and if we get an output, which is the addition of the outputs of those separately individual inputs, then that's one of the conditions for linearity. So that's called that the system is homogeneous, okay? And then if I can scale the input and the output is an scale version, equally a scale version of the same output that the original input produced, then that's the other condition for linearity. So just like with the analog systems, discrete-time systems are linear or can be linear in nature. So everything applies from that perspective. Big difference is we have discrete sampling times. So if we are discretizing or sampling discretely in time, we don't have differential equations. So the equations that relate to the system are not differential equations. They are what we call difference equations, because they are discrete differences in time. And an equation can be like the one shown here in 1. I can say that my output u of k plus 2 is equal to some constant b times u of k. So that's a difference equation. And what that means is that the function u, 2 sampling cycles from now, because I have k plus 2, 2 sampling cycles from now is going to be the constant b times the value of u now. So k is now. Okay? So that's a difference equation, and I can say that that holds for all k's greater than 0. All k's greater than 0. K equals to 0 is just a reference in time. I can make that whatever I want. It's just where my period of interest starts. When I want to start looking at the system or being interested in the system. So let's say that u of 2 is equal to, in this case, according to that equation, I can say that u of 2 is equal to b times u of 0. So that would be for k equal to 0. So I'm evaluating, this is a difference equation for k, so I can evaluate it at any value of k. And if I evaluate it at 1, I can say that this should be u of 3, actually, as a typo. U of 3 is equal to b times u of 1, because I'm evaluating at k equals 1. On difference equations, the order of the equation, which should be the order of the system that the equation describes, is the difference between the highest and the lowest indices appearing in the equation modifying the time sequence k. So in the case of equation 1, this is the highest index, 2. The lowest index here is 0, because k is equal to k plus 0. So this is a second order difference equation. And the order of my system is 2, or is a second order system. In this case, equation number 2, the highest index is 1, and the lowest index is 0. So this would be a first order difference equation, or a first order system described by that equation. The general form of any difference equation that describes a discrete time system takes this form. Equation 3 over here. The output as a function of the discrete time k is a linear combination of coefficients and values of k sampled at different times intervals. Now in here, as the most general form, the coefficients a are also a function of k. That implies that they are changing. And the most general form, that can be the case. But if the coefficients which describe the system, the a coefficients in this case that describe the system, are changing with time, then we have what we call a time variant system. So the very intrinsic characteristics of the system are changing over time. Those are systems that we don't want. We want systems whose characteristics are non-invariant with time. So an example is, if we have an electronic system, we don't want our parts, the characteristics of our parts, to be changing over time. We design something, we design some type of program, some type of algorithm, some type of circuit with some gain, some characteristics. We don't want any of that to change. That's called a non-time variant or a non-invariant system. So normally, these coefficients are not a function of time. They are constant coefficients. But the linearity still applies. In general, if I know for our n-order system, if I know the n number of initial conditions, and I have the difference equation that describes the system, that's enough information to derive the response of the system for any time after those initial conditions are available. If the initial conditions are at time 0, and I have a system that is first order, and I have the value for the system at time 0, and I know the input for 0 and after, I can predict the output for any time 0 and after. If the system is second order, I would need the first two values. How would that work? This is an example. Let's say that I have this first order system, because I can see that the highest index is 1 and the lowest index is 0. I have this first order system described by equation 4, and I want to find the response to a unit step function. So you know that the unit step function is 1 at 0 and thereafter, and is 0 before k, in this case, is 0. And I am given an initial condition, x0, this is the output, x0, where u is the input, the unit step. I'm giving that the initial condition, x0, is 0. Since this is a first order system, I know what the input looks like for all times, actually. And I know that at time 0, the output is 0. This is enough information for me to be able to get the output of the system for all times, in this case from time 0, which marks the reference time, or when I start looking at the system or being interested in the system. So I know what the output is at k equals 0. It is 0. But how about at k equals 1? At k equals 1, here I have minus a times the value at 0, we know that that's 0, and the value of the input, which is a step, at 0, which I know is 1. So at k equals 1, the output is b, a constant. B and a are constants. Then I can keep doing that. I can say for 2, I have minus a times the output at 1, well, that's what I just calculated, that's the previous output, times the input at k equals 1. But it's a step function, so that's 1. So I get this expression, which I can rewrite as 1 minus a times b. And I can do that for k equals 3. So k equals 3 is minus a times x at k equals 2, which I just calculated, plus b times u at k equals 2, which again is 1 because we're talking about a unit step function. And I get this expression and in terms of those constant coefficients. And can I just keep doing that? So this is a small example that shows that for an n-order system, if I know the initial conditions and I know the input, I'm going to be able to predict the behavior. Under certain conditions, if the system is linear, time invariant, and we're also going to talk about the system being stable. The system has to be stable in what we call the BBO sense. Bounded input, bounded output. What that means is that if I have a system where I put a bounded input, so my input is bounded by 2 real values, I'm expected to get some type of output that is also bounded. Not by the same values, but bounded. That's important. So my system is stable. So are our systems going to be described by equations like this, which are actually quite simple? No, but the ideas is what we want to retain. Stability, linearity, bounded input, spec bounded output, and knowing that if we know the input of the system and we know initial conditions, we should be able to predict future behavior. That's the mathematical idea that we want to retain, to use that on these complex systems that we're going to be looking at later on. So for discrete time systems, one tool that is very useful that we use a lot is the Ztransform. And just for completeness and to remind you, we're not going to be computing any Z-transforms or do any type of partial fraction expansions or anything like that. But it is a tool that has a meaning and a usage even with more complex systems. So digital filters, for example, that express and can be as transfer functions in the C domain. In fact, in digital systems that do digital signal processing, a Z minus one, a Z raised to the minus one operator is considered a register. It does the same thing as the register. It delays, it's a delay, it's a time delay of one sample or one clock cycle. So I'm trying to relate these things that you have seen before, mathematical ideas, to hardware that we're going to be talking about as soon as the next chapter. Also, there is a relationship of the Z-transform, because Z is a complex number. There is a relationship of that complex variable and the complex variable S of the Laplace transform used in continuous time systems. You can see that Z can be equated with e to the minus s t, where capital T is the sampling period of the signal that you are sampling for this discrete system. So much of the discussion that we're going to be having as we try to fit these complex systems to the physical processes is that these are domain-specific problems. So we're going to try to come up with complex system to solve domain-specific problems, and that's going to require multiple resources. We alluded to that previously, but the concept of the domain expert, the multidisciplinary nature of the systems, and that's going to have some implications about methodology, which is part of the course, talking about design methodology. So how do we address domain-specific system requirements? At the forefront of design methodology today are two camps. Classic systems engineering, so what you would find at Boeing, Massive Systems, NASA, they use a lot of the concepts of more of a pure systems engineering. And the other one is software engineering. So software engineering has become very mature in the methodologies that they use. But now we are talking about the next step. These are complex systems with complex software, with complex requirements, complex security requirements, complex real-time requirements. And we're going to start by drawing from those domains of systems engineering and software engineering. Why is that? Well, because we're still going to have systems engineering people in the team, and we're going to have software engineering. But the requirements, how to capture requirements in a way that we can distill domain-specific requirements that can be very foreign and unknown to the people that are going to put the system together, never mind down the line the people that are going to put the hardware together, and also the people that are going to write the software. when we're talking complex software, we're not, so to me, anything less than 50,000 lines of code, to me, really is not complex software, okay? So that's the type of, just to give you some quantitative threshold. So it's important, the methodology and the tools to go from this domain-specific requirements of this physical and getting to the cyber, this electronic systems that have this complexity with software, connectivity, security, and things of that nature. Why do we need that? Or why do we want that? Well, ad hoc methods produce waste because ad hoc is the antithesis of optimization in anything in general. So we can come up with things that are unnecessarily large, and that's a proxy for saying unnecessarily expensive. Normally, if something is large, you can use that as a proxy for cost. It could be hard to maintain and hard to test. So we're going to be discussing two things: how to manufacture products, how to test them, how to validate them, how to maintain them. Those are parts. Those are important parts and constraints of complex systems. So it is important to be able to come up with a way to manage all these requirements and be able to distill the requirements from the domain at a cyber-physical level, at the system level, software, hardware, and so on down the hierarchy of requirements. If you have a methodology, then you can measure quality. As an example here, software quality can be measured against different requirements. But normally, quality can be measured or is measured against criteria. And there are, on the software side, there are publications on what those criteria are. And you can find those at the site for ACM, the Association for Computing Machinery. And also the IEEE has a society dedicated to software engineering as well, okay? So these are some of the examples what criteria to use to measure the quality of software. There are a set of, you can measure if good engineering practices of software engineering practices are being applied, from the way that modularity is being applied, reusability, style, commenting is in there, and you can use other criteria like customer satisfaction, the rate or the outflow of latent bugs that come back after the software has been released, and the fulfillment of requirements at a specific release. So how much do we actually meet the requirements if we do an alpha release or a beta or pre-production or a production release? So not all the requirements are necessarily met with an alpha, but if you're tracking that and you want as a vehicle or quality improvement of your software development process to say, here's the number of requirements that we meet when we have an alpha release, and we want to increase that by 20% sequentially for the next few quarters, that is a way of tracking continuous improvement and the quality of your processes. So that being able to link the domain to things like our software engineering allows us to use the same tools to get better at the execution of our more complex systems. So, one of the things that I've said is that for these systems, we're not going to be relying on equations. We want to keep the mathematical ideas, and I'll keep coming back to that. But really, these systems are going to have to be modeled. And I am happy that there is a wealth of modeling infrastructures, and the industry is cooperating in that respect. And I'll tell you about a few tools later on. But as an example, something that is mature that can be very applicable is UML. I think that if you are a computer engineering student, I think they do teach UML in the software engineering course. Make sure that that's a wonderful tool. Make sure that it stays with you and expand it. There are, when I learn about, for example, just to give you an example, when I learned about use cases a long time ago, it was in the context of software engineering. And since I also had a good hardware background, I immediately saw that. I said, but this is something that must be used everywhere. So I immediately started using it, and we were designing chips, use cases, methodology to the chip design process in the part where I was responsible of. So things like that. Wonderful tools, UML, use cases. So that's something that lends itself more than equations to the type of systems that we are going to be discussing. So what is the first step if you're presented, or if your team is presented with development problem or development project in a cyber-physical system? The first step is to analyze the domain. The first step is to analyze the domain. I want to start constructing some type of flow, so when we get to chapter 3 and we talk about the actual design of our physical system, we're going to have a nice flow chart. But I want to start talking about those concepts here in chapter 1, which is really, in my mind, is kind of a review chapter. So the first thing that we want to do is to analyze the domain. And for that, you have to recognize that you may be maybe an expert or the guy that knows the most about cyber-physical systems because you took this course, and but you're not a domain expert. So the first thing to identify what are the relevant concepts, the relationships between the actors in the domain and the rules of functionality in the domain. In other words, knowing these things determines and specifies the domain boundary. That's going to become important. The domain boundary. So you can fit the solution to the problem. For that, you need a domain expert. You need a domain expert. You may be the expert of the process and the design and bringing something of your own background if what you really like is analog design, or what you really like is embedded systems or communications, you may bring that also with you. But if you are involved in the design of complex physical systems, then you're going to start with the domain of interest, where the system is going to provide a solution, and you're going to need a domain expert to define the boundary of the domain and the problem. So now, kind of a parenthetical few slides about a state variable representation. And we already talked a little bit about that, but I want to mention it here again. We have two ways of specifying models for systems. One is a state variable, which means that I know the characteristics and the behavior of the system internally. We're going to call that a state of the system internally. And then I'm going to express the output of the system as some type of function. And when I say function, I'm using that very liberally. Don't think of an equation. Think of a set of rules, algorithm, model, whatever you want, as abstract and as complex as you want it to be. But what doesn't change is the fact that the output, the system, what doesn't change is the fact that the system has a state now that defines its usefulness, its behavior, and the output is a function of that state. That is a state variable view. Also, the state of the system is changing because the system is dynamic and is doing something useful. If the state of the system doesn't change, then it's not doing anything. It's just a nice paperweight, okay? But the system, the state is changing. Given the present state, in other words, the future state is a function of the present state and the input. That description, which is a state variable description, applies to every system regardless of the complexity. We can put together those equations for very simple logic and very simple control systems, but that idea also applies to very complex systems. And I want that to stay with you. And then also, what applies is that if I know the state, the input, and the initial conditions, then I can describe the behavior of the system going forward. Another type of description is that maybe I don't really need or care for knowing the internal state of the system. I just need to express the system as an input to output relationship. So that would be an input-output model. But why would I want to complicate myself with a state variable if I just care about input-output? Normally, you just want to know that if this input goes in, the output comes out. Well, you really get maximum observability, maximum controllability, and the maximum ability to identify a system if you know the state. And it depends how you model. If you're modeling the physical world, which you don't have, it's just the way it is, and you want to interact with it and have a system that includes, so that's the cyber, that includes that physical world, then you want to understand the internals of that model. You want to have a state variable view of the system. So as a simple example, if you have, and you can pick the state whatever fits what you're trying to do. So the message here is that there is flexibility. There is flexibility. There is no one says that has to be the state. You pick according to what makes sense for the problem that you're trying to work. Now, something that is familiar, maybe familiar to you, is the coupled mass spring system. So you can say that in that system, the states can be the energy storage elements. So the mass and the spring, they store energy. If you have a electrical RLC circuit, then the energy storage elements are the inductor and the capacitor. So we may have less. We could select, in this case, instead of the mass and spring, we could select the velocity and a mass. Or select the elongation of the spring as a state variable. So they're not unique. In the RLC case, we could select the current to be a state, or we could select the voltage. The important thing is that we can relate all these quantities together, and we'll see that it can be done in a very elegant way, and the message that the equations, that the equations tell us as we take those ideas to complex systems is quite useful. And it's nice to see that there is that congruency from logic design, from control systems, from simple systems to more advanced and complex systems. So again, a state is that minimum set of variables that can describe the system at any given time. And if I know the input, if I know the state, behavior, and the initial conditions, then I can predict this future system state, and therefore the future system output, because the output is a function of the state of the system. Now again, this assumes that the system is time invariant, meaning that the dynamics of the system, the parts of it, what the system is made of, they don't change, or they're changing so slowly that for all intents and purposes, I can consider them a constant. Those A coefficients of the discrete system equation, they are constant. I also, for this to work, require that these are linear systems. And that means that no system is really linear, but either the non-linearities are very small as a percentage of the whole, or I can linearize the system around the area of interest that we're looking to do our design. Where we're looking to do our design. So in general, I can have a system described in this manner. I can have an input vector. I can have a system described by the state variables and the state equations, and I can have an output vector. Simple enough. Again, the state variables are the internal description of how the system works. Those are the state equations. And in classic control theory, we have the state and the derivative of the state. And this could be a set of first order or ordinary differential equations, and that represent the state equations. This is the first derivative of the state variables, or some type of linear combination of the state variables. Those represent my state equations. So if I have n variables, n state variables, I'm going to have n equations, and each equation is going to be the first order derivative of a linear combination of all the state variables. So that's the classic theory. Perhaps if you didn't see that in signals and systems, for sure, you would see that in the controls systems course. And these vectors, they're just a collection. And they're just a collection of numbers that we can write as a row vector, and then just say that we're going to take the transpose of that, so it becomes a column vector. And we can have that for the input, for the state, and for the outputs. And if we have the derivative of the state, then we just have to integrate and we can find the actual state. So that's simple enough. And there are nice hardware components that do that integration for us. So in the analog world, you have nice op-amp integrators, classically. And last time I was telling you how the same thing happens for state machines. That is really a state variable representation. A state machine in logic design is really a state variable representation where the flip-flops represent really the integration blocks. Represent the integration blocks. So essentially we have this derivative equation, which is a function of the state, the input, and time, and it forms a vector. And as I advance time, I can see a trajectory through time, but in the state space. Well, again, that's harder to visualize if you are not doing op-amp based compensators for control systems, which nobody does. But I think where you can see that is in state machine design. What is a state diagram? You remember that. What is a state diagram? Well, that is the state space time trajectory. Start at state 0. If this happens, I go to state 1. If this happens, I go to state 2. If not, go back to state 0. That is a trajectory in the state space as you go through time, as you go through the different clock cycles. That applies to, and that is very relevant to today's design of digital systems and also to the design of software. Because as I mentioned, a lot of software can be implemented as one of the ways, one of the tools and methods to implement some software, depending on the application, is as a state machine. So, but it's the same state equations. But perhaps we never made that connection. Now the other thing is that in classic control theory and state analysis, if the system is linear and time invariant, so we call that an LTI system, then these equations become ordinary differential equations with constant coefficients. So remember, the coefficients now are constant because this system is time invariant. And then we have this form, this system of state variables that says that the derivative of the state variable is essentially a weighted sum of all the state variables plus a weighted sum of the input vector. And we can separate that, and this expression is the same as this one, okay? So it's a matrix format, which is that the derivative of the state vector is a matrix times the state vector plus another matrix times the input vector. And this, more than the matrix representation, I like this more. For complex systems, what this tells me, I like it more because it's saying that if I identify the state of a system, if I identify the state of a system, the state variables, the derivative of that state, in a sense, what the system is going to do next, that's another way of looking at that derivative, is a weighted sum of all the state plus a weighted sum of the input. That doesn't matter what the complexity is, that is a way to look at system design and be able to come up with all kinds of applications of this idea, of this formulation, to be able to optimize systems. Because the A coefficients and the B coefficients, these are weighted, these are weights. And I can start looking at features and come up with relative weights that relate features and state and behavior of systems to what the system is going to do next and the output, because this is the output equation. The output is also a matrix, a weighted sum of the state variable plus another part to weight the input. So if you remember logic design, we said that D is 0 because we said the output only depends on the state, to simplify the design of state machines. That is also the case. That is also the case for some of the complex systems anyways. I'll show a couple of examples. One of UML, one of some other tool. If we can get there today. So everybody seems to be familiar, or at least UML, Unified Modeling Language, came about to aid software engineers describe complex software. So it became part of the toolbox of software engineering. It's an ISO standard. And the idea is that the diagrams shows relationships between objects of what you're trying to model. And then you can have activity diagrams that represent processes. So I'm going to go just as a review because I think that there are other tools, even though I like UML very much and use cases and things like that. There are other tools that are coming online that I think are lend themselves more to the design of complex systems. So, but I do want to cover this because it's something that you should know if you don't already know. Should have some minimal knowledge of UML. So these are the standard parts of a UML diagram. We have time signal, we have branching, send, receive, action, object, start, end, and branching or fork. So we can be branching or we can be so let's look at each one of them. So a UML activity diagram normally consists of nodes and edges. So it's event driven, so events occur on the nodes and the edges connect the nodes. So you can think of an activity as time progresses as a token going through the diagram, and if you are simulating the model in a UML simulator, then that's what's happened. You can traverse the activity diagram, and you can, if your model is sophisticated enough, if you know how to make these very useful models, then you can start looking for issues and problems, deadlock conditions, race conditions, things that are not addressed by the model that need to be comprehended and resolved, and so on. So all diagrams start with a node, start node, and end with an end node. And then we have some of this, an action, so a rectangle with the rounded corner, that's those are specific actions in the activity diagram. And normally you put something concise inside, something that says what's going on. Then we have the rectangle, which is an object, a component of the activity diagram. And these are sort of intermediate objects or storage of information. So that way you can move data or hold data, so you can pass that data from one action to another. Then you can have the diamond that denotes a division or a branch in the path, or a choice, and depending on some criteria, you can take one choice or the other. Then we have this black bar, which is really where different actions are coming in, and all the actions or all that is coming in needs to be present and available for the activity to go on. So in that way, it's sort of an AND function. If you're using it as a from many to one in that sequence, so you need all the inputs satisfied to go on the activity. If you're using it the other way, then basically you have many activities that go you have one activity rather that goes to multiple places. So in that sense, you can use it in both ways. And then you have the time event signal. Means that you're waiting for something, you're waiting for the time trigger of some nature, some event to take place for the activity to go on. So, very rudimentary, these are the elements of UML or UML diagrams, activity diagrams, that can aid with the description of complex systems or activities. And the next figure, I have an activity diagram, which essentially, now of course, if I had something really, really complex, it will take me a long time, but something that I think has enough complexity, but we can go through it in a couple of minutes, is the activity of an airplane landing and taking off again. So that's what this is, and it makes use of all these different elements. So you can see that at here's the start. The aircraft touches down, it waits for parking position. Now in this specific airport, you can go to a jetway, or if they're all occupied, then you can go somewhere and they'll take steps, and then you have to like walk to the tarmac, okay? So that's what this signifies. If you are going to be parked, you get there to the parking position, or you get to the ramp. Then once you get to either of those, the engine is switched off, the brake blocks are placed, and then three activities start. We start the power supply, checks, we unload the baggage of the passengers, and we start deboarding the passengers. This one specifically, when that happens, after we finish deboarding the passengers, that's when we can start catering for the next flight. We can clean, we can supply the water, and start refueling. Once we start the freshwater supply, we also start the wastewater supply, and when all this is done, we can start the boarding process for the next flight. What else is going on here? After we start unloading the baggage, we can start loading the baggage for the next flight. And after these two are done, and this one over here, then we can remove the brakes, power the engines, and again, if we are at a parking space, then we have to undock and start the pushback process. If we are at a jetway, we just go, we taxi to the runway, wait for the green light or for the authorization to take off, and we take off. So that kind of gives you an idea of how to use these different elements of UML on something that has some complexity to it. Now, a process, a system is complex. It doesn't have to be electronic but or electrical or computer in nature, but we are going to use it in that domain, and I hope that you can see how this can simplify and aid start visualizing solutions to the design of complex systems. So we're going to stop here, and I'll see you guys tomorrow at 4 in the other room. Okay? Thanks.